Welcome to our live webinar today. My name is Octavia and I'm from the marketing department. I'm here together with my colleagues Nadine and Max.
Hello.
Hello.
Nadine is the marketing product manager and Max is the technical product manager. Our today's webinar is about forging defects and how they can be avoided. Indeed, the prediction of forging defects is a main lever to optimize your products and the production chain by reducing prototypes, raw material, and of course, energy costs, particularly topical issue today. So after a brief introduction of our company, Transvalor, Nadine will bring it closer to the main topic and show you how forging defects can be avoided with Transvalor software Forge. After the presentation, we'll meet again for the question and answer session. So don't hesitate to type your questions in the question box, please, and we'll back to you later. So the cameras will be turned off now, and Nadine, it's your turn.
Thank you, Octavia. Then today it is my pleasure to welcome you to our webinar dedicated to the prediction of forging defects using forge simulation software. Before we start, just a few words about the GoToWebinar platform and how to operate the control panel. You can use the orange arrow here, that is here, to minimize the control panel to the right. By default, the microphone will be turned off for all the participants. At any time of the presentation, feel free to type your question in this area, and I will get back to you and answer these questions at the end of the webinar. Transvalor is a world-leading software editor providing cutting-edge solutions for virtual manufacturing. The company has been founded since 38 years ago. Transvalor contributes to the innovation of today and tomorrow. For example, in automotive industry, Transvalor solutions allow cars worldwide to run securely. We supply the manufacturing industry with a process simulation software, giving keys for rational engineering decision-making. We provided added value engineering consultancy and services to tackle new technical challenges that you might encounter. As well, we can help you to customize your processes. We work in very close partnership with CEMAF Minopari Tech Research Laboratory with more than 120 scientists, allowing research results to be integrated constantly in our products. Today, more than 1,000 companies worldwide entrust Transvalor with their material forming simulation needs. Internationalization is one of the biggest goals of our short-term and long-term strategy. We are strengthening our presence with the new offices to be near our clients and respond to their needs. Recently, we set new subsidiary in United Arab Emirates, China, and India. Our products are used worldwide in different industries, like energy, aerospace, automotive, heavy industry, as well research and several research institutes. For all our customers, we are committed to provide first-class simulation software and services. For those who don't know Transvalor, we propose different products to help you to manufacture your processes and increase parts quality and productivity. Our solutions can be used at any step of your production, from the foundry to the forming, until the heat treatment and the fatigue calculation. Here we see together the interoperability between all our software solutions. As well, we are working to the interoperability with external software to help you to easily integrate our solution in your production. The microstructure evolution is very important. You can model the microstructure evolution from the casting till the forming and under the fatigue calculation. Let's start with the outline of this webinar. First, I will start by showing how the simulation can predict closed-die forging defects. For example, underfilling, faults and lapse detection, piping defects, and proper grain flow. The second part is dedicated to the defect originated from the starting material, such as shear mark, central of looseness, and porosities. In the last part, some defects detected in cross-wedge rolling, extrusion, and ring rolling will be investigated. And I will finish with the conclusions and the perspective. The forging technology may look simple, but you know that it can be such a complex process. Several defects can appear, for example, cracks, and it can be on different location of the part. Then one of the challenges is to avoid different kind of defects, such the one presented in this image, like we see together. Let's start with the closed-die forging defect, for example, underfilling, faults and lapse detection, piping defects, and improper grain flow. The underfilling is a defect that appears when some section of the die is not completely filled by the flowing of the metal. Simulation software, like we see in this image, can be very helpful to predict this defect. Here we have a comparison of an example of where we can check the underfilling defect on the final part of the truck piston case. Coupled analysis provides real results of material flow compared to reality, as we see here. In the next slide, we will see another way other than material flow how to detect this defect. Then in our software Forge, we have a dedicated scaler, which is the scalar contact that is available in the result selector that can help you to detect the underfilling. Then you go to the result selector, you click on the contact, and the areas that are here in red, like we see in this image, indicate the zone where there is underfilling. As well, it is possible using the cutting plane, as we see in this image, then to cut the part with a cutting plane and to check the underfilling. It is possible to measure this underfilling by measuring the distance between the die cavity and the part. To go faster in the detection of the underfilling defect, the custom actions can be used. This feature is available from the version NXT 3.1, then it is quite recent. To create the custom action, you need to display the contact, then you click on the contact, you need to set your legend, and then export your visualization settings. Once the underfilling custom action has been created, you go to custom action and then you click on the underfilling. And now it is possible with a single click to check the underfilling on any simulation or any project. Let's talk about another defect, faults and lapse detection. Faults and lapse defects appears when two surfaces of the metals against each other being welded are not welded completely, like we see in this image. Here, a case of brass fitting is present. We see how the simulation can predict this defect. To the left, then here we have the experimental results, and to the right, we have the numerical result. In Forge, a point tracking feature is available to easily detect the apparition of any faults and lapse in the part. This feature allows the identification of lapse at each stage of the forging. As well, this feature helps you to follow and determine whether the faults move to the flash. Measurement of the depth, it allows the measurement of the depth of the fault. As well, thanks to these features, you are able to perform a reverse analysis and to understand the origin of the fault. Now, in the next slide, we will see together the point tracking feature. Then, to use this point tracking, you go to the ribbon and you click on the dedicated icon. We can see here that thanks to this feature, we can detect the apparition of the faults. In fact, points in red indicate where the material enters in contact with itself. We can notice in this ephemeral implant forging that the fault go into the flash. On the right, we see another example. Then this is an automotive part where we can check the apparition of in this area of the fault. Now let's see another defect, piping defect. How to detect piping defect or flow through in our software. Piping defect or flow through appears where the material is sucked at the end of the forging. In the case of extrusion, the potential causes of flow-through appearance are cavity entrance radius and the cavity width. In numerical simulation, you can use the underskin marking grid layer that helps you to detect its defect. Here, the underskin marking grid is in red. We can check the apparition of the fault in this corner of the piping defect and as well on the upper corner. As well, in 3D, we can check the apparition of the piping defect on the upper part here and on the corner of the part. Then, underskin marking grid is a very useful tool that helps you to detect this defect. In this industrial example, we will see as well the piping defect, how to identify this piping defect thanks to the marking grid. Here, the marking grid is in green, and we see the apparition of the piping defect in this area. Now, we will see the improper grain flow, how to check the grain flow. During forging, the deformation leads to the grain flow orientation. The grain flow lines of the metal may not be formed in the proper direction. The grain flow may not respect the specification needed to guarantee the part mechanical property. Here, for example, we see the specification needed in the head of the screw. And we can see the form of the lines needed to guarantee the SA/US-CAR8 specification needed in the head of the screw. Here we can see another improper grain flow. Now in the next slide, we will see together how to check the improper grain flow in a screw case forming. Then here's the example of forming sequence of a Hextox head screw is presented. Marking grid, like we see, is a very useful tool to detect improper grain flow. Now, then here we see how using marking grid we can follow the grain flow during the wall forming sequence, during the different steps of forming. Then here we can notice the continuity of the grain flow. And as well, we can notice that this grain flow respects the SA/US-CAR8 specification that we see before. Then it respects the specification needed in the head of the screw. Let's make a recap on the closed die forging defects. How to detect them and how to analyze if we have defects on this and closed die forging. First, then we can detect underfilling. Can be detected by analyzing context color. And to go faster in the analysis of this defect, it is possible to create a custom action. Then with a single click, you can detect this defect. To identify the faults, a point tracking feature is developed. And it is possible as well to use marking grid. To identify piping or flow-through defects, you can use underskin marking grid or as well analyze the velocity vector. The grain flow fibers allow to the detection and the avoiding of improper grain flow. Now we will talk about other defects, then defects that originate from the starting of the material. These defects appear due to the shearing operation, for example, or during the casting operation. The part here is made on 3 operations. a bar shearing, then first an upsetting and a second forging step, the block. Here we present the result of the, and we can see the shear is the effective strain obtained after shearing. The effective strain increased during the shearing operation. Due to the shearing operation, we can check here that the quality of the sheared surface is not uniform. And we can see very well that our results are in very good agreement with experimental one. To check if the shearing operation caused the apparition of a high residual stress on the final part, we have the possibility to use the marking grid to track the sheared surface. In this example, the sheared surface were tracked by defining a marking grid on gray, like we see here on this image. We see the evolution of the sheared surface during the upsetting operation. And here we see the evolution of the sheared surface during the blocker stage. Now let's check the central looseness if we have. Poor central quality may lead to rupture or cracks on parts during upsetting. Then to follow the central looseness, natural fiber can be used. You can, in one click, create the cylinder defining its radius. While forging the crankshaft, the central looseness is followed to guarantee the quality of the part. Now let's make a recap on how to detect defects that originate from the starting material. The shear mark tracking can be done by using marking grid. This is very useful to check if the improper shearing operation caused the apparition of high residual strain on the final part. Central looseness that leads to ruptures on parts during upsetting can be identified using the natural fiber. We didn't talk about the porosities, but it is possible to track the porosities during forging. Thanks to the direct export from tear gas to forge, it is possible to follow the evolution of the porosity and the carbon concentration during the forging simulation. Several user variables are available in Forge, such as Yamanaka or Niyama model that help you to detect the porosity or the hot tearing. In the last part of this webinar, we will check other defects that appears in other applications, for example, cross-wedge rolling or extrusion or ring rolling. During cross-wedge rolling, a cylinder billet is rolled in the cross direction between two wedge-shaped tools, as we see in this video. Several defects may appear during the cross-wedge rolling. This is due to the tool geometry. The torsion of the part may happen during this process, and this can be detected using a marking grid. Here we can see that we define a marking grid in the black with the lines, and we can see the apparition of the torsion on this final part. Function of the cross-wedge rolling tool parameters, then function of the angles that are using of the tool, several defects may appear. For example, Mannesmann defect, sliding, or section reduction. In the next slide, we will see how we can detect these several defects. In this example, we use to detect these defects, the damage criteria that we use is Latonoco-Croft normalized. In simulation 1, the cross-wedge rolling conditions are close to the risk zone. Then internal cavities can be observed, as we see here on this part. Here, we analyze the results obtained numerically. We can see that we have a hot critical value of 1.5 that is present on the center of the part, showing the presence of risk zone. In simulation 2, the cross-wedge rolling tool's parameters leads to the sliding defect. Here we analyze the form of the final part, and we obtained by the numerical simulation And we can see the sliding defect that is present on the final part. In simulation 3, the crosswatch rolling tool parameters lead to the section reduction defect. Here, the diameter of the rolled section has been reduced from 22 mm to 11.5 mm. And we can check that in the center, we have a very important value of Lattencroft of 3, which may lead to a breakage of the part. Now we will talk about a defect that appears usually in extrusion. The chevron defects are the cracks that appear in the central of the extruded part, as we see here. Chevron defects are formed when the material moves faster at the boundary of the part than at the center. Numerical results can be used to predict this defect, as we see in this video. In this example, the damage criteria that has been used is Lattencroft normalized, and we can see that our results agree very well with the one obtained in reality. Here, a case of cold rolling of a steel bar is presented. These cases has been provided by Christophe Vichet of UGT. Then thank you. To detect the surface defect, we use the Lemaitre uncoupled criteria, and we can check here that the form of the defects agree well with the one obtained in reality, as well for this one. Now let's talk about another process, the ring rolling. Let's check defects that may appear in ring rolling. Then here we have a L-section ring rolling case that is provided by Pusan National University, and that is described in the following article. If you need more information, I invite you to read this article. The aim of the study was to detect and improve the defect that appears during the L-section ring rolling process. The major defects that occur during this process are the unfilling, and as well as the groove that appears on the bottom of the part. Here we see the evolution of the metal. In this image, we see the evolution of the metal during ring rolling process. After the second contact, the blank corner is not in contact anymore with the driven roll, which causes the unfilling and the apparition of the groove. The lower part of the part is compressed by the bundle of the driven roll, and the bending is caused to generate this groove that we see. Numerical results are similar to the reality. Then how to remove this unfilling defect? By increasing the height of the blank corner and the flange angle of the blank by 3 degrees, the underfilling can be removed. As well, by increasing the depth of the groove of the driven roll, the groove depth decreases from 0.77, as we see before, to 0.4 millimeters. The numerical simulation is a very good tool to investigate techniques to detect the defects, and as well, thanks to the numerical simulation, you can improve or eliminate defects. Several defects can occur during crosswatch rolling process. The Lattencroft damage criteria can be used to detect menacement and breaking defect. Metal flow can be used to check sliding defect. The marking grid can be used to identify the torsion. In extrusion process, chevron defect may appear. This defect can be detected by Lattencroft damage criteria. In cold bar rolling, a surface defect may appear. This one can be detected using Lemaitre damage criterion. In ring rolling, the unfilling and the groove are two defects that can be detected by the metal flow and the contact scaler. Now we arrive to the end of this webinar. Forge, let's make a recap. Forge can incorporate several tools to detect defects. The marking grid used in the detection of the faults, piping defect, and improper grain flow. As well, in Forge, we can use the results such as the contact to detect underfilling or point tracking to detect faults. The porosity can be analyzed to detect piping defect. To check the crack evolution of the first principal stress and the triaxiality stress are available. Forge incorporate several damage criteria. Some of them are coupled with the rheology, such as the Lemaitre, and others are uncoupled. We have several. We have Oyane, Rice-Tracy, Lattencroft, Brozo, and much more. Interoperability between Tailcast and Forge allows to follow the evolution of the porosity and the carbon concentration through the forging simulation. Thank you for your attention.